Hello, everyone. Come on in. While we're waiting, since I'm running a little late, you're welcome, of course, to ask questions. Last time we did chapter 17, if I remember correctly. Yeah, 17, and I said largely, sorry about that. I was leaving those exercises on ideal gas law to you. I might actually a little later on make some more and just post them online, more examples on my YouTube channel. But I'm under the impression, based on asking everybody in my other classes as well as this class, that everybody's had some experience with PV equals nRT and therefore knows how to use it. The main thing is, normally in physics, we use the ideal gas constant being 8.314 joules per mole Kelvin. There's, of course, two other versions that are often used in chemistry, but that's for different systems of units. And then finally, I told you about how there's something called steam table thermodynamics that a lot of engineering majors take. And in those thermodynamics courses and some other engineering ones, they use an ideal gas constant that's a different value for each particular gas you use. So basically what they've done is they've incorporated the molecular weight into the R value so that you don't have to look up molecular weight too. So anyways, that's why you might run into a little bit of difficulty if you look at engineering thermodynamics compared to what we do in physics or chemistry. So while I'm yawning, does anybody have any questions? All right. Well, what we're going to do today is we're going to start chapter 18. Ideally, I'd like to finish it, but I don't think I'm going to, because it's kind of some neat things in here. But it's the kinetic theory of gases, and the kinetic theory of gases basically is a way to work out statistically what macroscopic variables do. So I told you about how a system can be some part of the universe. Everything outside of that system is called its environment. And then there's rules and definitions of terms about ways the system can interact with the environment. So for instance, if you were be able to create an ideal thermos or an ideal cooler, then you might actually be able to prevent any heat loss from inside of the cooler to the outside, in which case everything in the cooler plus the cooler itself would be your system. And that system would be considered adiabatic. And that means that heat cannot flow in or out. If you had a system that maintained a constant pressure, then it would be called isobaric, for like the bar, which is a unit of temperature that you probably heard of before. There's isochoric, which means it maintains a constant volume, and various other terms like that. So there's a lot of little bold print terms in these chapters that you need to become familiar with. And I really don't usually take the time to explain them. One, because you should have heard them before, and two, because they're pretty straightforwardly defined. Okay. We'll learn about variables like entropy, which is what's necessary for us, or I shouldn't say it's necessary, but it is a ramification of the second law of thermodynamics. And we're going to learn about the first law of thermodynamics as well first, which is really just another statement of the conservation of energy. There's the zeroth law of thermodynamics, which basically says, hey, if A and B are in equilibrium and B and C are in equilibrium, and that means thermal equilibrium, then A and C are also in thermal equilibrium. So they sort of didn't really think that through, and they got the first law of thermodynamics, and they're like, well, we haven't really shown the others, so they made that the zeroth law of thermodynamics. I really wish I could stop yawning. This stinks. Anyways, one thing I want to remind you folks, as always, if you have a whole chapter or especially a whole section of a textbook named after a particular law or group of laws, like Newton's laws or Kepler's laws or thermodynamics in general, there's a high probability that you should probably commit those laws to memory. Okay, so yes, I do expect you to know not only Newton's first, second, and third law, but exactly which one's which. What's Newton's first law? What's Newton's second law? What's Newton's third law? Gauss's law, what's that? Or how about the first law of thermodynamics, or the 0th law of thermodynamics, or the second law of thermodynamics? All those are laws that we expect you to know. And in some cases, you'll see there's numerous versions, and you should probably know all of them, because us professors and instructors, when we're teaching, we often sort of consider questions like that low-hanging fruit. So sometimes we'll try to do a favor to our students and say, these questions are worth 17 points each, and one of the questions is state Newton's 3 laws of motion, or one of the questions is state the 0th, first, and second law of thermodynamics in the proper order and label them. So that's some of the kind of stuff we do. Another one is, for instance, state Gauss's or state Maxwell's equations. One, in fact, what I had in grad school was state Maxwell's equations, specifically in Gaussian units, which is the units that I used in grad school, and use them to derive the boundary conditions. That's a very typical problem, and it's not that hard of a problem. And the instructor gave it to us as 20% of our exam grade, as if that was just the sweetest thing ever. And it was, if you knew it. But if you didn't know it, then you're like, well, that's really kind of nitpicky. But no, it's not nitpicky. I mean, it's literally like the crux of the whole course. So keep that in mind, folks. So now that I've got a lot more people in here, I'm all the way up to 11. Woohoo! Anybody have any questions yet? How about you, Georgie? I just saw you come in. Do you have any questions about any past material or anything?
No, I'm all good.
Okay. So this chapter, like I said, is on the kinetic theory. And if you read in chapter 18, it starts off telling you a lot of the rules, and I should probably put my glasses on to make sure I can see this, a lot of the rules about what we're making assumptions of. So what we're going to do is we're going to list a bunch of sort of rules, if you will, that we think atoms / molecules are going to behave according to. And then from that, we're going to derive an expression that is very much the ideal gas law. So here's one of them. There are a large number of molecules, capital N, each of which has a mass m, moving in random directions with a variety of speeds. This assumption is in accord with our observation that gas fills its containers, and in the case of air on Earth, is kept from escaping only by the force of gravity. Okay, so we expect atoms and our molecules to constantly move in some kind of random directions. And that's because when we look at a gas, if you take, say a gas that fills up a 16-ounce cup or a 16-ounce bottle, and you open it up in a vacuum room that's maybe 8 foot by 8 foot by 8 foot, and then you open it up, even though it was a vacuum, that air from that 16-ounce bottle will fill the whole room. And that doesn't make any sense unless the molecules and atoms are constantly in random motion. Okay. 2, the molecules are on average far apart from one another. So remember what I talked to you about, the solids are usually on the order of a couple radii from one another. That's sort of their sweet spot, and they're stuck in sort of some sort of lattice, and they're vibrating about that spot where they're comfortable. And then liquids are maybe a little bit further apart, but at least far enough apart where they're not holding on to one another like they do in a lattice, so they can roll across each other like BBs in a barrel. Okay. So in this case, we're assuming they're really far apart and much more than the average diameter of them. 3, the molecules are assumed to obey the laws of classical mechanics and are assumed to interact with one another only when they collide. Although molecules exert weak attractive forces on each other between collisions, the potential energy associated with these forces is small compared to the kinetic energy, and we therefore ignore it. Okay, so as long as you're willing to treat the individual atoms or molecules like perfectly rigid billiard balls that have no gravitational or electrical attraction to one another, and they sort of don't, because it's such a small order of magnitude compared to how fast they're going in their kinetic energy, then you have something approaching what I was talking about as an ideal gas. And then finally, 4th, collisions with another molecule or with the walls of the vessel are assumed to be perfectly elastic. like the collisions of perfectly elastic billiard balls that we studied in chapter 9, we assume the collisions are very short duration compared to the time between collisions. Then we can ignore the potential energy associated with the collisions in comparison to the kinetic energy between the collisions. So that's sort of the big picture that we're looking at when we're talking about ideal gases. We're saying that's what we think atoms and molecules are going to do. And then we're going to work out statistically, mechanically, using Newton's laws of motion and stuff like that, what individual atoms should do, not looking at any particular atom, but just saying on average what an atom should do, and then sort of sum up the average of all that and look at the overall effect of there being, N, capital N, of those atoms or molecules in the gas. So that's the really big deal. So the first thing I want to do is I want to turn the camera on my document so that I can help you see sort of the derivation that we're going to go through. And the derivation is basically going to start off thinking again about balls moving through space. And what we're going to assume is a ball has been constrained to, and this is one particular one. In fact, there's actually, multiple ones. I'm going to say this is my x-axis. I'm going to say this going into the page is my y-axis, and this going up is my z-axis. And I'm going to say there's a box. And it seems unarbitrary because I'm going to choose the box to be cubical. But in fact, you can do a more thorough treatment with it being any shape you want. I'm going to assume it's L by L by L. So this will be L, this will be L, and this will be L. Okay, so there's our little box. It's somewhat transparent because in reality, it's just a construct, and it actually could be like a piston, if you will, holding a certain amount of space. And what you'd see is there's all sorts of little atoms and molecules running around. I think I discovered that green kind of stunk on here, so I'm going to use red. And I'm going to say, well, here's an atom. Here's another atom. There's another. There's another. And again, I keep saying atoms, but really this could apply to atoms or molecules. And each of those, of course, have some random velocity in some random direction. So this one could be moving that way. This one could be moving that way. This one could be moving that way. This one could be moving straight out. That one might be moving straight down. All sorts of crazy stuff, right? So what we want to think about is, well, I'm trying to get a picture of, say, the pressure on a particular wall. Let's say this wall over here. Well, if I look at that box, and specifically that particular wall of that box, so here's the wall right here. Okay, obviously the box goes on this way and this way. If I imagine my individual atom as if it were initially over here, but ends up here, I might think, oh, well, what happened was the ball was here, the atom, if you will, was here, it hit the wall and then bounced off that way. Okay. So if I think about that just in terms of the X component, now ignoring the fact, I mean, there's truly a Y component here. The Y component goes up and continues to go up, but because there's no friction and stuff like that, that Y component speed is not going to change at all. Whereas the X component speed totally changed. That's an entirely different scenario. So what I'm going to try to work out is what actually happened. So what I'm going to say is I'm going to say the change in momentum, and remember momentum is m times v, the change in momentum, delta mv, would actually equal m times v sub x, where x is just that component of velocity in the x direction. That's finally, notice I'm going to the right in the final. So in the final direction, it's actually positive, minus m times negative v sub x. And since it's a perfectly elastic collision, you'd expect that vx and this vx to be the same, because perfectly elastic, the wall, it means one, the wall was not moving. We had not considered the wall moving at all. So 2, the only thing that was really moving in this collision was the mass. So 1/2 mvx squared is the initial kinetic energy. And the final kinetic energy, at least in the x direction again, is 1/2 m. In this case, let me write it this way. I'll use my eraser here. I bought these fancy pens with erasers, and I keep forgetting that I even have them, that I even have an eraser on them. And this one's going to be negative v sub x squared. Obviously, if kinetic energy is conserved, that means they're equal, but that's also what happens when a negative is squared. So you can see that the actual change in kinetic energy is going to be twice the mass times the velocity in the x direction. Now, if you think that on average, you can sort of pretend like the average velocity might be Vx. Later, we're going to deal with that and actually work out a Vx. But what you realize is for a given x velocity, this thing is going to cross, a molecule or atom is going to cross the length of this box in the x direction fairly regularly. And in fact, the amount of time between adjacent collisions should be equal to basically twice the width of the box. So notice it could collide, and you'd immediately, right after it collided with this wall right here, you'd start the timer, and it would go boom, and it would bounce off here, and then it would come all the way back here. And just before it hit the wall again, you'd stop the time, and that amount of time would be 2x over v sub x. Does that make sense to everyone? Now, that is the time between collisions, and that helps us because if we were to know, for instance, the mass of the atom or molecule or whatever, and the average velocity, we can figure out how many of these suckers are hitting the wall every second, and then add all that effect up, and that total force would, once divided by the area, would give us the pressure on that wall. So that's really what we're shooting for here. And in fact, if we use, I don't know if y'all recall this, but Newton's second law, summation forces equals mass times acceleration, was the way we originally learned it. But I told you, in fact, what Newton said was the total force is equal to d by dt of the momentum. Well, that's the momentum, is that delta mv. So we can say F, which is really, again, just an abbreviation for the total force, is equal to delta mv, and this is all in the x direction, of course, over delta t. So now from that, we get the total force acting is delta mvx over delta t, which is 2 mvx over, now delta t is 2L over Vx. So immediately we have the 2's canceling out, and we get m v sub x squared over L. And that's due to just one molecule or one atom. Does that make sense to everyone? Anybody have any questions about that? Now, again, I'm saying this is a total force, but by our assumptions, we're assuming that atoms and molecules either only run into other atoms and molecules or the wall. So it really is the force acting on the molecule. It's really the only force on the wall. So you don't have to call it the total force. You can just call it F, meaning the force on the wall. And I mean the wall of the container. Does that make sense? Now, that's not going to alter its x component. In fact, we find that the x component doesn't change, just like the y component. Remember, this one had a y component, and it probably, or excuse me, a z component, and it might have even had a y component, my y component being into and out of the page, and my z component being parallel to the page but up. So those aren't going to change either, whether they hit a wall or not. So really all we got to do is start thinking about, okay, well, how does that compare to all of them? Well, for n particles, what that means is the total force and that's total force for, whoa, need my eraser again. The total force for in atoms / molecules is F is equal to, now what we had was basically a common factor of M over L. So I'll write M over L, and then I'll write Vx1 squared plus Vx2 squared plus ... plus Vxn squared. In other words, I just have to add that up for all the N atoms or molecules that we're dealing with. Does that make sense to everyone? Anybody have any questions on that? Well, now what we're looking into is we'd like to figure out some way to apply statistics so we can get some sense of what on average molecules and atoms are going to do. Well, if we took the average x velocity, what we'd find is 0. And the reason why is because basically you have just as many particles moving to the right at 123 meters per second as you have moving to the left at 123 meters per second. And that's sort of just the law of large numbers. You know, if you have literally 10 to the 23rd atoms and molecules, there's a whole bevy of velocities, and every one of them is going to have a match in the opposite direction, more than likely. And in fact, it would be quite rare for any one to have a unique velocity. Because of that, we don't want to take the average of the velocities. What we want to take is the average of the squares of the velocities. And if you took the square root of that, that would be called the root mean square velocity. So what I'm going to say is I'm going to say the average velocity squared. So it's in other words, the average of all these little values, it looks like a bigger V here. It's not necessarily intended to be, but the average of all these should really just be the sum of all these divided by the number of all of them. If you do that, then you get, okay, well, the average of the squares of the velocities would be Vx1 squared plus Vx2 squared plus ... plus Vxn squared. So that's all N particles. And now I'm going to divide those N particles by N. And now I have the average of the squares of the velocity. Well, that's nice, because now I can replace my little Vx1, you know, that's really what I had up here was Vx1. I had the velocity for one of the particles. I can now say, oh, well, the total force is actually going to be that M over L that we had already. And instead of just taking one particular velocity, all I have to do is multiply it by N by that one particular velocity. And now I have the total force. Okay. Now here's the kicker. Basically taking that number multiplying by N is what got me this. Okay. And that's the sum of all the velocities, you know, the average velocities times N. So I now have the actual force. But guess what? There's something called the equipartition theorem, and the equipartition theorem, here it is, I think it's QUA, if I remember correctly, partition. Even though I almost always pronounce it like equal partition, I don't think that's correct. Equipartition theorem. Anybody have a correction for me on that in case y'all happen to have read recently or something? What the equipartition theorem says is basically, if you have a buttload of numbers, and I'm not talking like a buttload, like, you know, how many dollars Elon Musk has. I mean like a real buttload, like how many dollars would a mole of Elon Musk have? Okay, so that's what I mean by a buttload. So when you have a buttload of numbers, there's no reason, or a buttload of atoms or molecules, there's no reason to believe that more or a larger fraction of that number would be going in the x direction than is going in the y direction than is going in the z direction. In fact, you expect that the average square velocity in the x direction is exactly equal to the average velocity. The average of the square velocity in the y direction is equal to the average of the square of the velocity in the z direction. So because of that, you'd say, oh, well, v squared, which equals vx squared plus vy squared plus vz squared, those three each should be the same, and they should just be what we call vx. So that'd be vx squared plus vx squared plus vx squared. That's 3vx squared. So by using that, I can now say that v squared, and this again is really the square of the average velocity, the average of the square velocity should be in fact 3 times vx squared on average. So now I can add that in, and now I have F is equal to m over L times n times not just Vx, because that's in a particular direction, but the average of the squares of the velocities divided by 3. Now, what we know is the pressure, which I'll go ahead and explain to you guys because you haven't necessarily had, well, you had the ideal gas law to some extent. So I just want to remind you that pressure, I was thinking for a second that I was dealing with 241 for a second. Pressure is equal to force divided by area, which in our case, since I made that a perfect cube, I could say it's F over L squared, or I could just call it F over A and just say, maybe this is an L and maybe that's not L, but the product of the two gives me A. But either way, I'd say that the pressure, which is equal to the force divided by the area, is in fact equal to, and you can see where it gets more general now, it's going to be equal to 1/3. Now we have M, or N, I should say, times M times the average of the squares of the velocity divided by A times L. Well, A, which really is it's the same as this area, so I'll highlight this one. A is the same as this area because we were really treating that area over there. If we called that A, then you see A times L is clearly the volume. So we can say, oh, well, P times V is equal to 1/3, and then N times the number of atoms or molecules, in other words, times mv squared. Okay, now that mv squared is really nice, but it's not really something we're used to. That mv squared has no physical meaning, but if I were to multiply by 2 and divide by 2, then I could get something cool. And in fact, when I do that, when I multiply by 2 and divide by 2, I can say PV is equal to 2/3 N. There's me multiplying by 2. Now I'm going to divide by 2 times 1/2 mv squared bar. Okay. Well, that happens to turn out to be the average kinetic energy, doesn't it? So 2/3 of the average kinetic energy is kind of a useful quantity. We'd say the average kinetic energy, I'm just going to write it K now. The average kinetic energy is 1/2 mv squared bar. Does that make sense? And we already learned that PV, remember the end of last lecture, we learned that PV is equal to N times K times T, where K is that Boltzmann constant. Remember, K is also called K sub B, which is really just the R over Avogadro's number. And what we found was another version of the ideal gas law was PV equals NKT. Well, check this out. I've got PV equals, so combining these two, I've got PV equals N times what I say is 2/3 1/2 mv squared average, but it's also equal to N times KT. So we found a new expression. We found that the average kinetic energy is in fact equal to 3/2 KT. Does anybody remember where that 3 came from? Anybody remember? It's still on the page. It's on the screen so you can see it. Anybody remember where that 3 came from? Oh, my weird pinky just happens to be randomly oscillating in some particular direction. Wonder. Anyone? Okay, it's the number of degrees of freedom. If you treat an atom or molecule as if it's a point particle, it can only move in 3 dimensions. It can only move 3 different ways. So really a more general response might in fact be that 3 is the number of degrees of freedom. In other words, if we do a similar calculation and we try to take into account the fact that not only can my atoms move left, right, in, out, and up, down, we also take into account that as a molecule, they might actually be able to spin about 3 different axes. That might get us 6 degrees of freedom. And if they could vibrate around a couple of axes, along a couple of axes, maybe that might get us 7, 8, 9 or more degrees of freedom. So that's just something to keep in mind. But right now what that tells us is the average kinetic energy of the individual atoms or molecules in a body of temperature T is 3/2 KT. And that's what I meant when I told you the modern definition of temperature is that it's a multiple of the average kinetic energy of the molecules and atoms that make up the object you're studying. So let's do an example. We've got this. Does anybody have any questions about this derivation I just did? Okay. So this will actually kill a couple birds with one stone. So what I'm going to do is I'm going to do an example where we're going to make use of, say, the ideal gas law, but we're also going to make use of that equation. And we're going to say, what is, so here's our example. One, a room is 5.00 meters by 3 meters tall by 2.5 meters. Actually, let's say 2.5 meters tall. That might make a little better sense. And is at a pressure of 1 atmosphere. Let's say that's 1.00, so I can do 3 sig figs. if it is known to contain about 1,800 moles, I'll say 1,800.0 moles of air, A, how many are O2 molecules? B, how many are N2 molecules? C, what is the temperature of the room? And that was C. Let's say D. What were the average kinetic energy of each of those types of molecules? Okay. Does that make sense to everyone? What we're going to do there? All right. So what we know here is we have, in principle, a volume. We have a pressure. So I know the volume is going to be 5.00 meters by 3.00 meters by 2.50, even though I didn't put a 0 there, meters. I know that the pressure P is equal to 1.00 atmosphere, which is 1.01 times 10 to the 5th Pascal. I do not know T though, and that is one of the things I'm asked. But I do know that N, the number of moles, is equal to 1,800.0 moles. I do not know the average kinetic energy of the O2, and I do not know the average kinetic energy of the N2. So does everybody have some feel for what we're trying to work out here? Hopefully that should make some sense. Okay, so in order for us to figure out, these last two parts, clearly we got to use the 3/2 kT thingamabob, which technically speaking, it's kind of rough to use the 3/2 kT thing for O2 and N2, just from a weird standpoint, in that some of the energy, well, I shouldn't say it's wrong. It is correct because we just calculated the center of mass kinetic energy, but in fact, temperature only depends on those kinetic energies, the ones where the center of mass is moving left, right, in, out, or up, down. So I guess that's acceptable. So let's start off with part A. So part A, I ask, how many O2 molecules are there? So there's 1,800.0 moles. Anybody recall roughly what percentage of the air is oxygen? Anybody? Now, there's some arguing point. You might say, well, is that 20% of air is, I don't know why I wrote Q there. Is that 80% volume, or is it by mass, or is it by count? Well, obviously there's some difference, but the good news is O2's mass is like 16 and N2's mass is like 17. So there's not a huge difference if it's mass as opposed to something else, right? So yeah, O2 has a mass of 28 and N2 has a mass of 28 and O2 has a mass of 32. So that's really not that big of a difference. So now we're not going to worry about it. We're just going to assume that roughly the count is about 20% of the number of moles. In other words, 20% of the 1800 moles is O2. So we'll say 0.20 times 1800 moles is equal to, trusting my old calculator here, I'm going to say 0.2 times 1800, which you all should be able to do that in your head, of course, is 360 moles of O2. But I didn't really ask for the number of moles. I asked for the number of molecules. So that means 360 times Avogadro's number. So I'll say times 6.022 e to the 23rd. So I'm going to say that's 2.17. That's close enough. 2.17 times 10 to the 26. And that's MOL for molecules, not for moles. I know there's some confusion in that, but that's what I mean. Part B asked how many N2 molecules there'd be. So again, I'm just assuming that that's 80%. Again, we know oxygen's maybe more like 19%ish, and maybe nitrogen's closer to like 78, and then argon's nearly a whole percent, and water vapor and CO2 and all those other things are really way under 1%, but this is close enough for us. So I'm going to say 0.80. Obviously, you're going to divide that by 100 to make 1%, and then you get 18, and then you multiply that by 80. That would be 800, which would be 8,000. 8,064 should roughly be the number of moles. So I'm going to say 0.8 times 1800. Again, not necessarily the way that was meant. Whoa. Oh, that's what it is. Okay, so it's 1,440. So just ignore whatever those words were I said, because clearly the rails fell off at some point. Now that's going to be 1,440 times Avogadro's number, which is 6.022 e to the 23rd. So I'm getting 8.67 times 10 to the 26th molecules. This time I'll put a C on the end, so it's a little more obvious that I'm talking about molecules instead of moles. So we've done part A and part B. That actually might come in handy, but really the main thing was I wanted you to realize, hey, there's no such thing as an air molecule, right? There's molecules that are in the air, but there's no such molecule called air, okay? So I wanted you to remember that the atmosphere is in fact a mixture, not a compound. So we've now started working the solution. That was part B. Part C is, what is the temperature of the room? Well, according to the ideal gas law, PV equals nRT. So that would mean T is equal to PV over nR. Well, in this case, we already know the number of moles. We know the pressure. So that's 1.01 times 10 to the 5th Pascal. By the way, remember a Pascal is a Newton per square meter. 1 PA equals 1 Newton per meter squared, because that's going to help us when we start to work out the units of this. The volume, on the other hand, is 5 times 3. Well, 2.5 times 5 is nice because that gives me 1250. And then multiply that by 3, that gives me 3750. So that should be 3750. But just in case, I'm going to multiply 5 times 3 times 2.5, and I'm going to get 3750. And that's cubic meters. And obviously that's an extra sig fig. So I'll say 37.50 cubic meters. Notice a Pascal, which is a Newton per square meter, cancels 2 of those out and just leaves a Newton times a meter up there, which is a joule. So that comes in handy. Rn is 1800 moles. And now I don't know why I wrote that as a moil. Probably my Judaism, I guess. No, I'm not really a Jewish person, but still, it's the only word I know moil relates to. So it's 8.314 joules per mole Kelvin. So now you can see this mole is going to cancel out with that mole. I said we had a Newton meter up here, which is a joule, so that's going to cancel out. And I'm going to have a Kelvin in the bottom of the bottom, which means ultimately I have a Kelvin on top. So when I do this, I say 1.01 e to the 5th times 37.5 divided by, here's where I use parentheses. If you don't, you're going to make a mistake. 1800 times 8.314. And that gives me 253.087 Kelvin. Obviously, these are extra sig figs. So about 253 Kelvin. 273 Kelvin is freezing. So that's a kind of, I guess that's a kind of cold room, right? So any questions on that? We're not quite finished. All we've gotten so far is just the temperature, but now that we have the temperature, we can actually use that to try to make some sense of what exactly is the speed of those things. Okay. Actually, by the way, I'm looking it up. Yeah, just for your records and for your knowledge, I should double check. The 20% and 80% is really supposed to be based on the mass. So that's 20% and 80% by mass. You have to account for that by taking into account the fact that one oxygen is about 16 U's and one nitrogen is about 14 or 15 U's. Actually, it's like 14.99, whereas oxygen's like 15.99 or something. Let me double check. Oxygen, no, I had it reversed. Oxygen is 14.0067 and oxygen is 15.9994. All right, so we got that. We've got this answer. We've got this answer. And actually, let's highlight those a little bit so they're easier to find in our notes. That temperature was quite a bit lower than I expected to get, but here we are. So what I want to know now is part C, what is the temperature of the room? I did do that. And then part D, what was the average kinetic energy of these? Well, when you go to calculate the average kinetic energy, what you need to know is what is the mass, because the average kinetic energy, D, K average, is equal to 3/2 kT. Right? And I don't necessarily want to know just the kinetic energy. I'm going to add a part E to that. I'm going to say, what are the speeds? And what I mean by that is what's the average velocity? So I'm going to do that as well. But we can first start off by finding out what the average kinetic energy is. So the average kinetic energy is just going to be 3/2 kT period. Notice that has nothing to do with masses or anything like that. So I can just type that in and say 3/2 times, remember the Boltzmann constant is 1.3807. You don't really have to memorize another number there. If you already know the ideal gas law, 8.314, you just have to divide that by Avogadro's number. And that's 1.3807 times 10 to the negative 23rd joules per Kelvin. And then times the temperature of 253, and I'll carry one extra digit, Kelvin. So this is going to give the kinetic energy of both of those, which, by the way, obviously doesn't change at all. And that's sort of the point. The oxygen molecules, which, you know, one molecule is going to weigh about 32 U, whereas the nitrogen molecule, one molecule is going to weigh about 28 U. They're both going to have the same amount of kinetic energy. That's sort of the whole point, right? So the bigger atoms are going to go slower than the than the lighter atoms. So if I do this, I'm going to go 1.5, because that's what 3/2 is, times 1.3807 e to the negative 23 times 253.1. And I get 5.24 times 10 to the negative 21. And that actually gives me joules. So what that says is each N2 molecule and each O2 molecule on average have 5.24 times 10 to the negative 21 joules of kinetic energy. Now remember, that's 1,800 moles of that stuff. So really, if you want to get an idea of the total amount of energy, so I'll say total energy in that room, I'm going to take and multiply that by 1,800 times Avogadro's number. So I'm going to say times 1800 times 6.022 e to the negative, or excuse me, e to the 23rd. And that's going to give me 5.68 times 10 to the 6th joules of kinetic energy. That's 5.68 megajoules. That's just the energy stored in the kinetic energy of the atoms, well, in this case, molecules mostly, of that room full of gas, even at that low 253 Kelvin temperature. That's a buttload. Now, the cool part is, let's find out how fast the actual oxygen and the actual nitrogen go. Well, what we know is that kinetic energy is equal to 1/2 m v squared bar. So v squared bar, if I take the square root of that, I will get, in some sense, VRM, or an average, which we call v root mean square. So what I'm going to do is I'm going to solve for v squared bar, which is 2k over m. Okay, that's what I get when I solve for v squared bar, but now I've got to take the square root of that. So that's really what it's going to be. So I'm going to take the square root of 2 times, again, this is average kinetic energy, So that turned out to be 5.24 times 10 to the negative 21 joules over. Now here's where I'm going to say O2. So the mass of O2 is really going to be 32 times 16.0 U, and of course 1 U is 1.660. I'll just call 1.66 times 10 to the negative 27th kilograms. Okay, remember oxygen is 16. Excuse me. Remember oxygen is 16. I don't know why I put 32 there. I was doing that instead. So I really have to do 2 times that because it's O2. So this will give me the average, in some sense, the average speed of an individual O2 molecule. So I'm going to take 2 times, I'm going to scroll up there and grab that 10 to the negative 21 number because I can with my big screen calculator. Okay, so I grab that. And now I'm going to divide that by, and here's where I use parentheses to be safe. 2 times 16 times 1.66 e to the negative 27, close parentheses. That's what's under the square root. Now I'm going to take the square root of all that, square root answer, and I get 444 meters per second for O2. Now I can do the same thing for V root mean square into, it's going to be 2 times 5.24 times 10 to the negative 21 joules over 2 times 14.0 U times 1.66 times 10 to the negative 27 kilograms. Square root of all that. I think you can see the difference is this one's divided by the square root of 16. So if I multiply this number by the square root of 16 and divide this and then divide it by the square root of 14, I'll get the right answer. So I'm going to say times square root, and now I'm going to get rid of the 16. So I'll put 16 on top. Whoa. Divided by 14, and that'll give me 474. Actually 475 meters per second or into. So notice, yes, the lighter molecules did in fact go somewhat faster than the heavier molecules. Any questions on that? If you, a good example, your book does something like this, so I'm going to do something like it too, just to give you an idea. Root mean square and average are not the same thing. If you want to see that, whoa, Nelly, that went badly. I just bumped into my whole setup and messed up everything. Well, not too bad. A little higher than it should be. And this is this way, and this is this way. Okay, that's pretty good. All right, so let's imagine the numbers. I want to take some very specific numbers and calculate an average, and then I'm going to take some very specific numbers, in fact, the same very specific numbers, and calculate a root mean square. Just so you'll see a difference and actually understand in some sense the difference. Let's say our speeds are 2.0, 2.0, 3.0, 3.0, 3.0, 3.0, 5.0, 8.0. Okay, let's do some crazy stuff like that. So if these are V's and they're measured in meters per second, then the average velocity would be 2 plus 2 plus 3 plus 3 plus 3. I did 4 threes plus 3 plus 5 plus 8 divided by 1, 2, 3, 4, 5, 6, 7, 8 divided by 8. Again, your calculator has packages to do this, but it's not worth your time to do that in this case. So 2 plus 2 plus, I'm going to say 12 because that's what 3 times 4 is, plus 5 plus 8. And I'm going to divide that by 8. That becomes 29. Hopefully somebody can verify that they got 29 as well. And I get 3.625 meters per second. Of course, we only had 2 sig figs, so these two are extra, so it should be about 3.6. Now let's calculate the root mean square. The root mean square would be 2 squared plus 2 squared plus 3 squared plus 3 squared plus 3 squared plus 3 squared plus 5 squared plus 8 squared, and all of that divided by 8, but then you take the square root. So when I do that, I'm going to get 4 plus 4 plus 9 times 4 is 36, at least in my world. 5 times 5 squared is 25, and 8 squared is 64. So I got 133 divided by 8, and then take the square root. So I'm going to divide that by 8, and I'll take the square root of that answer. Okay, evidently I'm having a hard time putting the answer in there. Square root of that answer. Let's see. I got 4.077. And notice that also has units of meters per second, which is good. But notice how significantly different this is. 4.1 versus 3.6. That's a huge difference. So that's just to keep in mind that root mean square and the mean are not the same things at all. Now, with that in mind, there's this neat little derivation, which we normally learn in like a junior year of a physics program. Actually, I shouldn't put an example on this. And it's called the Maxwell-Boltzmann distribution. So if you work out statistically all the possible ways you can distribute, say, atoms or molecules within a sample. Remember, our sample is any particular, our samples, any particular part of the universe. You could sort of divide up the universe or the sample into all the atoms / molecules that have this energy, maybe kinetic energy. And then right next to that are all the ones that have atoms or molecules in this energy band, and then this one, and then this one, and then this one. And in fact, you can do that until you literally go up to an infinite number of different energy bands. And then you can work out some statistics and play a little bit of mathematical tricks. And what you find out from the Maxwell distribution is specifically that, and I'm trying to read it exactly the way it should be read, and it's specifically f of v is called the Maxwell distribution of speeds and is plotted in figure 18.2. So in other words, this number fv gives you a distribution of speeds, and the formula is, and this is one you definitely want to have written in your equation sheet, but it's 4 times pi times n, where n is the total number of atoms / molecules you have. All of that, 4 pi times n, is then multiplied by m, the mass of the individual particles, divided by 2 pi times the Boltzmann constant times t, all of that raised to the 3/2 power. So that's basically you take the square root and then cube it. And then all of that times the square of the velocity times e to the negative 1/2 mv squared over kt. Again, that's Boltzmann constant. Okay. So what it means is it's the quantity. If you multiply f of v times dv, so you take f of v times dv, then what you end up finding is that you get that many molecules, number of molecules with speeds between v and v plus dv. That's it. Okay. So in other words, if you integrate it over all space, you'll find the total number of molecules in general, which obviously should give you like n. But if you integrate it from, say, v equals 3 meters per second to v equals 300 meters per second, then you'll get the number of molecules that have speeds between 3 and 300 meters per second. That's really what that is. Now, if you make a plot of this graph, this is a sort of famous plot, and it's sort of an important plot. And sometimes they plot it as a function of different variables. But generally speaking, what you find is that the high velocity end sort of falls off rather quickly, and the low velocity end not so much. So it sort of goes like this, reaches a maximum, and then falls off rather quickly. And if you actually plot some things, like if you want to plot the average velocity, that would be just plain v bar. If you want to plot the root mean square, just like we saw before, that happens to be slightly larger than the average velocity, which is what we found. And then you can also plot, of course, the most probable, which technically should be at the peak here where the slope is 0. And that is VP, the most probable. So like I said, if you integrate this from 0 to infinity, you better get just n, because that's really all the possible speeds you could have. So that's one check. And that's actually, in reality, when you go and derive this, that's the way you figure out what this constant is, because that's the answer that spits out. So you have to use the 4 pi and all this junk just to make it work out. But anyways, if you want to compute this, it's not that hard. For instance, if you want to calculate the average velocity is really just you take the probability of it having such a velocity, which is this quantity, and you multiply it by the quantity you want it to have, which is v. So the average velocity, in fact, is just the integral of v, f of v, dv, and then you divide that by n. Well, that might sound really awful, and it's not pretty, but if you have a good table of integrals, it's actually not that bad. You can see that the 4 pi n over n is just going to cancel out and give you 4 pi. And then you'll find out that you've got the m over 2 pi kt to the 3/2. That looks god awfully scary, but look at it. It's just a bunch of constants, and none of them have v in it. So they don't make the integral any more complicated. So all you're really left with is an integral symbol taller than that, of course, is an integral of v squared e to the negative 1/2, or actually it's v cubed because it's already v squared, v cubed e to the negative mv squared over 2 kt. And that all times dv. if you look up in a table of integrals, or you can actually use integration by parts, which is another neat little trick. I highly recommend you taking the time to do this by integration of parts. But if you actually do it, what you'll end up getting is the square root of a, and by the way, I did do this on my YouTube channel, so you can look at the derivation there, but you'll get 8 over pi times kt over m, which is approximately 1.60 times the square root of kt over m. Remember what we had before? We had the square root of kt over m. Actually, I think we had the square root. What was it? Square root of 2 kt over m. Yes, the square root of 2k. Actually, I didn't solve it that way for you, but yeah, you could have seen that 1 over mv squared. Yeah, you would have had a slightly different number than 8 pi, and you can see that that's the average velocity. If you wanted to know the most probable, you'd say df of v over dv, and you set that equal to 0, and that would give you that vp. This one right here is actually, and this is another exercise I highly recommend you doing. This one turns out to be the square root of 2 kt over m, which is approximately 1.41 times the square root of kt over m. If you did set 3/2 kt equal to 1/2 mv squared bar, and then try to solve for v squared bar, you get v RMS is equal to the square root of, notice the 2's cancel out, you'd get 3 kt over m. This one we got 8 over pi. This one we got just plain 2. But you can see from our normal derivation, we got 3 kt over m. And of course, if you actually take the time to do the root mean square, you will get exactly 3 kt over m. So in other words, if you integrate this, notice you have to calculate the square. So you'd have to put a square here. So v root mean square would be the square root of the integral of v squared f of v dv over m, like that. That will in fact give you 3 kt over m, which is what we found from a much, much, much easier way. All right. Any questions about that? All right. Well, we're about 3 minutes shy of class being over. So I'm going to leave it at that. I will tell you that we did make some approximations by assuming those things that I read to you. There's ways in which you can avoid making those approximations. For instance, there is van der Waals equation, which says that P plus A over, in this case, I'll use volume divided by the number of moles. I don't know why I wrote it in there, M there. Volume divided by the number of moles squared. So instead of PV equals nRT, they'll do P plus all this times V over N minus some B, where you have to actually experimentally determine A and B. And that happens to be equal to RT. So that's van der Waals equation. And that's all lowercase, by the way, until you get to the W. So that's van der Waals equation. And believe it or not, that is actually fairly used. Like I took a triox course, basically a mixed gas courses for scuba divers, where you can be certified to breathe not only air, you can breathe nitrox, you can breathe triox, you can breathe heliox, all that stuff. And this is one of the courses you have to go through, and you actually have to use van der Waals equation sometimes in dealing with that, because you're dealing with such high pressures and low high densities that the stickiness of the adjacent atoms becomes an issue, and that's what these takes into consideration. It takes into consideration that atoms and molecules actually have a physical size and actually have an affinity for each other. So anyways, that's really, believe it or not, we've essentially completely finished chapter 18. You can look at some more examples if you'd like. Mean free path, you'll definitely see some homework on that, and I consider those homeworks completely fair game, but I think when you see the practice test, you'll get a better idea of what I'm expecting of you. So you guys are free to go. Thanks for coming, and I'll wait for the last one to get out. Yeah, 21% might be right, Georgie. Thank you. Victoria, do you have any questions? I'll wait a couple seconds.
No.
Okay.
Sorry.
No problem. Have a good one.
You too.
Bye-bye.